Hello, what is going on? Welcome back to Data Diving Dude. Today we're going to be talking about League of Legends. We're going to answer the questions, what are the most important factors in a game of League of Legends? Is there a way you can predict whether you won or lost a game of League of Legends based on only your team's data? And is there a way to kind of identify which of these sub-objectives are most important? Now, you might not understand all the statistical stuff that I use in this video, and I'll try to touch on everything a little briefly, and try to put it in a concise way to where even if you don't really have a deep knowledge of statistics, you can understand what I'm talking about. But I'm also going to make other videos where I talk more in depth about some of the statistical methods I use, in case you want to get a little more information, if you're a little confused, or just want to kind of dive a little deeper into some of the methods here. So, League of Legends, the objective is to destroy the enemy's nexus. But there are other, I guess you could call them secondary objectives that make that objective easier, such as killing monsters in the jungle, killing the dragons, killing the Baron, killing the Rift Herald, getting kills in the other enemy team, stuff like that. And are there different types of dragons that are more important? Is like getting the Rift Herald important, getting multiple Rift Herald, getting multiple Barons, stuff like that? Or getting double kills, triple kills, quadra kills, pentakills, are they most important? We're gonna see. So the main method I use is a decision tree, and we're gonna get to the final model here below. But the thing I wanted to isolate the most important variables. So first I did a generalized linear model with every variable. And this it gives you a probability of winning based from 0 to 1. So like basically a percent chance of winning as a decimal. And I found that gold was really the most important variable. But there's a problem with using gold as a variable. You get gold from beating other objectives. And usually, obviously the team with more gold has a much greater chance of winning, and that's what you found here. But gold doesn't really tell us which objectives are most important. It's just like, okay, accumulate gold. Like, okay, there's a lot of different ways you can accumulate gold. You accumulate gold by killing minions, monsters, the enemy team, everything. You get gold. So you also get some gold passively with some certain items, or I think I don't know the actual thing, so I'm not gonna go into it. But gold's just not a good standard to use. So I decided to drop gold. Especially gold difference and stuff. I decided to just drop all of that. And I looked at another method here. I looked at a random forest of decision trees. So it just put a bunch of random decision trees with our sample, actually 50 of them. Looked at the most important 15 non-gold related variables. The most important one is deaths. And the second most important one is the number of Barons the opponent gets. So if the number of Barons the opponent... It's actually more important that your opponents get less Barons than you get Barons. Then assists, kills, so on and so forth. Now, some of this kind of makes sense intuitively, especially if you have an understanding of the game. Barons are a late game objective. If you get and especially the Baron is useful for pushing onto the enemy's base and nexus. So you're going to get a dragon instead of a Baron if you have the opportunity to get either one, if you're not planning on doing a push on the enemy's nexus. Especially if it's an Elder Dragon, which is another late game objective. And it's more like a kind of an overall buff, whereas the Baron buff is more for besieging the nexus and pushing lanes and stuff like that. Well, that's as far as I know. I don't play League of Legends very much, so I could be wrong about some of the stuff I say, but this kind of makes sense. Like, obviously getting these late game objectives are more important to wins, and it kind of makes sense because early game objectives can snowball into late game objectives, and the late game objectives kind of stand out. So anyway, our final model is this. This is our final decision tree model, and it only looks at 3 variables: deaths, barons, and how many dragons the opponent team gets. Now we're going to have another model where we just look at what our team does. But let's look at this model first. This is with all the variables we have. So if you have less than 12 deaths, so okay, well first I should start here at this top node. This top node means if you knew nothing about the team, no stats, we would just say it won. And you'd be right 53% of the time with our training data. And I forgot to say earlier, we split 80% of our data goes to building decision trees, 20% goes to testing. So in our training data, most teams, the majority of teams won, 53%, which, you know, you want it to be around 50-50, but this is fine. This 53% is fine. Okay, it's a little weighted towards the win, but it's fine. You're never going to have a perfect sample. Now we look at deaths. If we just only know deaths, if you have less than 12 deaths, you win 91% of the time. If you have more than 12 deaths, you lose 81% of the time. That's what this node means. If you got less than 1 Baron, you lose 96% of the time. So just knowing 2 pieces of information already gives us really good accuracy of predicting whether team wins or loses. If you have more than 12 deaths and a Baron, it's about 50-50 odds. But if you add a number of dragons the opponent gets, you win 84% of the time if you hold them to less than 3 dragons, but only win 36% of the time if they get 3 or more dragons. So you might be thinking, well, how accurate is this decision tree model? Only knowing 3 things: deaths, barons, and the opponent team's dragons. It's actually pretty accurate. We actually get 88.8% accuracy. Which is actually really good accuracy. It's not perfect. I think you want... I don't know what the actual perfect accurate number is, but you kind of have a general idea of somewhere between like high 70s, 80s. You don't want too much higher than that because you're probably overfitting, which means it's not... Number one, your model might not be practical in terms of runtime, because it might be too complex. And number 2, it might just be only tailored toward this pro match data and not actually apply towards the population of League of Legends games as a whole, which is what we're trying to predict. So, and obviously our sample coming from only pros, like, kind of skews it a little bit, but it was the only data they could get, so you gotta do what you gotta do. So that's what this accuracy means. And this confusion matrix, I'll explain. This confusion matrix means, like, how many did we get right? So on the left is our prediction, on the top is the truth. So we predicted 318 teams would lose that actually lost. We predicted 45 teams would lose, but they actually won. We predicted 39 teams would win, but they actually lost. And we predicted 348 teams would win, and they actually won. So that's pretty good accuracy. If it was like a perfect 100%, that'd be a problem. It means we definitely did overfit. It's not a good model to use. There's gonna be some error in this, but that is our tree model right there. So the most important variables are deaths, barons, and opponent dragons, and using those, we can tell if you win with 88.8% accuracy. Now, I'm going to run this, but get rid of all the opponent's variables and see what can we do that with. Let's use our dragons here. Can we only use our match statistics, not knowing their dragons, to see if we win? And it turns out yes, but instead it throws in double kills. So if we go here, the same things, everything's the same except it's double kills. So if you have less than 2 double kills, but also fit all these other conditions here on the tree to get to this path, if you have less than 2 double kills, you lose 70% of the time. But if you have 2 or more double kills, you win 72% of the time. Let's check our accuracy. Okay, our model actually gets more accurate here, 89%. So just knowing our statistics, only knowing our only knowing our team stats, we can predict if we won or lost by looking at deaths, barons, and double kills, and that's it. And we're accurate almost 90% of the time. That's crazy. I kind of want to play a few games of League of Legends and see if this actually holds up. But I just want to explain some of this stuff. So we have 98% accuracy, 95% confidence interval, which means the true accuracy of the model is we're 95% confident that's between about 87% and about 91%. So pretty tight interval there. The wider interval, a little more error in that accuracy. No information rate means if you knew nothing about the group, we would just say they won, and that's that 53%. 53% win rate. You'd be right 53% of the time because we had more groups that won than lost in our sample. And then our p-value is basically saying how much better is our model than the no information rate, than that 53%. And this means it's significantly better. It means the statistically correct way of saying this is that there's basically almost a 0% chance that our accuracy was this high by mistake. But if it was like 0.1, like 10%, it means that basically we had a bad sample and there's a 10% chance that our model is just straight wrong. So our model looks pretty good here. So yeah, only knowing deaths, barons, and double kills actually gives you really good insights onto whether or not a team won League of Legends. And remember, these are just pro games. So and we want to extrapolate. We want to build something that we can extrapolate to the overall League of Legends game database, let's say. But at least in these pro games, we can just build a model like this. So yeah, I'm gonna have to watch some Pro League of Legends with this in mind.